Modern language models can hold millions of tokens in context and write flawless, isolated functions. Yet, when tasked with an end-to-end software migration, that exact same system collapses under its own weight. This chart illustrates the findings from the 2026 Slop Code Bench. While agents achieve near-perfect success rates on single-turn code generation, their ability to navigate long-horizon, multi-step checkpoints drops to a 14.8% completion rate. The models possess the necessary syntax and logic to write the application. The failure occurs in the continuity. They cannot sustain execution over a prolonged timeline. 2025 and 2026 research identifies this behavior as context anxiety. When faced with an expanding context window and complex constraints, the model actively works to truncate its own output and exit the task prematurely. Prompting an agent to simply try harder or think step by step is an instruction, not a barrier. Managing complex software requires mechanical constraints that physically prevent the agent from stopping early. An AI agent's default state is efficiency. The underlying architecture is optimized to generate the stop token and terminate inference as quickly as acceptable parameters allow. Simply giving the model a larger compute budget to think longer does not solve the problem. In knowledge-intensive tasks, unbounded test time scaling causes the model to overthink, lead to degraded performance and hallucinated dependencies. This is where Unlazy operates. It is an explicit completion discipline skill designed to structurally neutralize model laziness. Rather than managing work with fuzzy linguistic checklists that the model can talk its way around, Unlazy traps the agent inside a rigid, verifiable state machine. Engineering at this scale requires forcing the AI's compute through physical enforcement layers, scaffolding that literally refuses to accept unfinished code. The depth tree method begins with a full compute budget in one root node. Standard workflows divide attention, fragmenting the budget into tiny slivers. The depth tree duplicates the budget, dropping a complete block into every leaf. Through budget forcing, effort multiplies with depth. This specific hierarchy prevents the agent from rushing to the finish line. Because the subtasks are structurally isolated, the model cannot see the end of the project, preventing it from optimizing its way out of the work. This aligns with documented research on architectures like S1, which artificially lengthen reasoning by forcing the model to wait when it attempts to stop prematurely. The depth tree guarantees that the final layer of a complex database refactor receives the exact same untruncated reasoning focus as the very first layer. Defining how a subtask actually reaches completion requires the second pillar, ledger-driven development. Before writing code, the agent authors the acceptance ledger, defining exact gates to prove the work is finished. Normally, models grade their own homework, hallucinating success metrics. This ledger blocks that. The check parameter relies on host shell scripts to verify artifacts, removing LLM assumptions. For qualitative outcomes that scripts cannot measure, the ledger requires the agent to supply specific evidence, like raw data samples or specific log output. The system scales the volume of this required evidence based on the complexity of the file paths being modified. These checks run with ambient file system, network, and credential access. This is an open environment, not an isolated sandbox. Moving validation out of predictive weights and into the deterministic host shell strips the model of its ability to lie about task completion. When the agent claims a gate is met, the host shell takes over the execution loop. The first strict requirement for success is the process exit code. If the script exits with any status other than 0, the gate fails. The second requirement is output validation. The standard output printed by the shell must perfectly match the exact expect string declared in the ledger. When it fails, the agent cannot talk its way past the block. It has to read the failure, write new code, and test it again. It runs the cycle until the deterministic check produces the 0 exit status and the precise string alignment. At that exact moment, Unlazy generates an evidence block. It permanently logs the working directory, the resolved shell, and a fingerprint of the execution path. This unfakeable evidence record ensures that parent-level tasks can fully trust the verified state of deep, nested leaf tasks without needing to re-execute them. Scaling this across a repository introduces a new risk. When multiple agents work on deep leaf tasks simultaneously, their file modifications can collide. The enforcement mechanism handling this traffic is the Claude Code stop hook. The stop hook scans the active ledger. If an agent reports completion with unmet gates, the hook intercepts it with a hard block. To manage parallel work, Unlazy establishes isolated pipelines. Leaf tasks run simultaneously only if they claim mutually exclusive file paths. This setup creates rolling dispatch. When a verified leaf finishes its checks, it automatically unblocks the next ready leaf, bypassing central master agent intervention. This conservative file lease matching provides the strict safety guarantees required to scale autonomous engineering across entire codebases simultaneously. This chart maps the complete integrated pipeline: ledger creation, budget-forced execution, system-level verification, and evidence recording. It takes the initial intent, distributes it across the depth tree, forcing the compute down to the leaves, and extracting verified evidence before allowing the system to proceed. The entire pipeline operates in isolation. It requires no conversational intervention or human supervision to enforce standards. We are moving past the expectation that a sufficiently large neural network will magically figure out the right workflow on its own. Unlazy represents the necessary evolution in AI software development. We are migrating from linguistic prompting to strict, verifiable state machines. Raw inference generates code, but deterministic discipline builds software. We cannot scale our way out of model laziness simply by stacking more compute. We have to engineer our way out of it. The depth tree and the gate contract function as the baseline structural requirements for autonomous work. The future of software engineering belongs not to the smartest models, but to the most uncompromising deterministic scaffolding.